Okay, here we go. So probability. This, for some of you, may be something you've seen before, but for some of us, it won't be. This is effectively, probability is the math that underlies statistics, right? Probability is a set of mathematical tools for understanding how likely an event is to occur, right? So how often, on average, does an event occur? That's the fundamental question we're asking with probability. The probability of X is how often, on average, X occurs. Probability is a set of tools for describing randomness. And probability helps us sort signal from noise, right? That is, it helps us detect patterns in data and determine what is meaningful and what is not meaningful. So we have two core theories of probability in statistics that we'll be dealing with. The first is a frequentist theory, and this is the classical theory of statistics, right? Frequentism is the kind of dominant theoretical approach to statistics, and it's the kinds of methods that are involved in most typical statistics courses. Is overwhelmingly what you see in statistical research. So a frequentist perspective on probability suggests that probability is the proportion of times an event occurs if we repeat an experiment under the same conditions many times. The basic assumption of a frequentist framework appeals to the central limit theorem and suggests that if we repeat an experiment or we repeat an event many times, the probability of an event will be the average of times that event occurs over the number of times we ran the trial. Right? But it assumes this kind of model of a large number of repetitions of an event and what would happen on average during those repetitions. So let's consider a simple experiment, right? We're largely going to be working from the frequentist perspective. Just to introduce it, the most common alternative perspective to this is a Bayesian perspective, which thinks not so much about repeated events, but thinks about information. Thinks about information relative to what we know before we begin the experiment and what we learn after the experiment, and updating our information. Come on.
No, somebody help me.
All right. I'll take my 6. No, you're good. You're a good Lord. Of course, see you. Let's ask this. Let's kind of examine a frequentist experiment. What's the probability of obtaining a heads on a single fair coin flip? So what's the chance that we're going to get heads on a single coin flip? 50%. So I'm going to write a little R function to flip coins. The flip is going to flip X numbers of coins one time with a 0.5 probability, right? So it's going to come up as a 1 half of the time and a 0 half of the time, right? It has a 50% chance. Our binomial means random binomial, and a binomial distribution allows us to draw sequences of 1s and 0s. So we'll see the binomial distribution more when we get into logistic regression next semester, but we're going to just kind of assume it for now. So that's the binomial distribution, and we're going to recode it. So if else flip equals 1, it'll become heads. If flip is not equal to 1, it'll become tails. And it can only take on 2 values, 0 or 1. We're going to return flip. So this is like a pretty simple custom function in R. It's going to take the value of X, where X is the number of coins I want to flip. It'll draw from a random binomial distribution X, which will be the number of coins I want it to flip. And then it will convert that vector into heads and tails and return the vector. All right, so let's see what we get. If I flip 1 coin, in this case, I got a heads, right? If I run it again, I might get a tails. Heads, heads. Hey, I got 3 heads in a row, right? And if we want to think about the joint probability of obtaining 3 heads in a row, right? We won't get there yet, but that's 12.5% chance of observing that event, right? Heads, heads, heads. But that's also true of any distinct sequence. So what, in this case, from these three observations, what is the average probability of obtaining heads within these three trials? It's the sum of xi, where xi equals 1 when the coin is heads, divided by n. So we have heads, heads, heads. So that's 1, 2, 3. So the numerator here is 3. The denominator here is 3. So the average is 1, right? So here, just based on this small n experiment, if we don't know what the probability of flipping a coin is going in, we do, but let's assume that we don't. We're just kind of flipping these coins to see what happens. Based on these three trials, we might say, oh, well, it's always heads. But what's the problem here? Why is our inference wrong? We want to guess what the true probability of a heads is, and we've guessed 1. Why are we wrong? Because our n is too small, right? We haven't repeated the experiment enough times to get meaningful information. So let's flip 5 coins and think about the probability as being the average outcome under repeat experiments. So what I'm going to do is I'm going to flip 5 coins, and I'm going to sum up how many heads there are, and then divide it by n. Right? So I'm going to flip 5 coins, count the number of heads, divide it by 5. In this case, I got 60% of the sample, or 3 out of 5 were heads. So you could imagine this being heads, tails, heads, tails, heads, or something like that. 3 heads, 2 tails is what this function returns, and then I divided that by 5. What about 20? As my n grows, the estimated x bar, right? So we could think of what the central limit here is suggesting, where x bar equals sum x n k over n, right? X bar is our sample average. What we're showing here is that as n approaches infinity, x bar approaches the true mean, right? So when we take the limit as n approaches infinity, this is the central limit theorem, or the law of large numbers, kind of both work through this. As we approach a large n, x bar converges to mu, where mu is the true probability of flipping a heads, right? Once we get to 5, we get a 0.6, 20, we get a 0.5, 50, we get a 0.6. We know 0.5 is the truth, right? Once we're at 1,000, we get 0.509. Once we're at 10,000, we get 0.49964, right? And we could keep going, but once we get to a sufficiently large number, it's going to be indistinguishable from the truth. It's going to be centered. It's going to have its average centered around the truth. So we could think about representing kind of at any or any n, x bar mu will be equal to x bar plus some error term, right? And the error in this case will just be driven by random sampling, right? We could randomly draw, in this case, we drew 50, which is a pretty big number. We still randomly were wrong by 0.1, right? So in this case, our error was 0.1. That's our sampling error, right? Every random process will be characterized by some degree of sampling error. We can see what happens as our n increases, especially think about the jump from 50 to 1,000 to 10,000. What happens to our sampling error as our n increases? So we go from 50, it decreases, right? So we go from 0.1 error to a 0.09 error to like a 0.0003 error, right? And if we were to go up to 1 million samples, the error would decrease further, right? So with a large n, we can converge on the true value of the probability. This is the basic frequentist principle. When we repeat an experiment a large number of times, our sample average will converge to the truth. Or our sample average, our estimated statistic, will converge to the population parameter, right? What we've estimated from the data will converge to the unknown population parameter. Why simulation is cool is because we can define what that population parameter is and then run the experiment and see what happens. Okay, so also when someone says simulation and statistics, this is simulation, right? It sounds like a big complicated thing, but it's really just running a hypothetical experiment many times. And this is all the code you need for an experiment, for a simulation, right? Statistical simulation is not that complicated. It's effectively just running a process on a computer. So even though it sounds like a big fancy word, when someone says simulation and statistics, all they mean is they drew a bunch of random numbers and then looked at what happened. Okay, so frequentist probability, right? If nx is the number of heads and nt is the number of coin flips, the probability of heads is approximately equal to nx over nt, or as nt approaches infinity, we get the exact probability. Yep. So x bar, right? You could say x bar is approximately equal to p of heads, and mu is equal to p. So our sample average will always be approximately equal to the probability with some error, right? But as n approaches infinity, we will converge exactly on the probability. Okay, now Bayesian probability, by contrast, suggests that probability is a subjective judgment about the likelihood that an event occurs. So it's our best guess about how likely something is to occur. And it is a subjective judgment. 0 means the event never occurs. 1 means the event always occurs. In practice, the coin flip experiment is one where it's quite easy to repeat it many, many times. Let's think of a vaccine trial. Could we repeat a vaccine trial an infinite number of times?
Yeah.
Not really, because we're going to run out of people at a certain point, right? The population of people who are willing to participate in a vaccine trial will eventually be gone. And the cost of running a vaccine trial an infinite number of times is also prohibitive, right? So this appeal to repeat experiments, we'll see this more when we get to statistical significance testing, but this appeal to repeat experiments, Bayesians will argue, makes sense in some contexts, but makes no sense in a lot of applied contexts. And so a Bayesian is going to suggest that the best we're doing here is we're making a subjective judgment about the likelihood that an event occurs. To do so, effectively what we do is we take our prior beliefs, that is how likely we think an event is to occur before we collect data, and we multiply that by the likelihood that an event occurred after we observed the data using a statistical model. The product of those things is called the posterior, and that's what we draw our inferences from. We're not going to do too much with Bayesian inference here, but it's a really important philosophy of thinking about statistics. Effectively, we could think about probability as being either our belief about how likely something is to occur, or an absolute number that is determined by infinite repetitions of a particular experiment, right? The frequentist proposal is that there is a finite defined value of a probability that we could observe under hypothetically infinitely repeated experiments. The Bayesian approach is one that kind of prioritizes information. It suggests this is our best guess about how likely something is to occur based on what we've seen before and what I've seen in my data. So one is a kind of appeal to repeated experiments. One is about available information. If that doesn't make sense to you now, that's okay. But I just want to kind of point these two out. You're going to hear these terms used. So the Bayesian approach is more interested in understanding uncertainty in terms of available information. The frequentist approach thinks about uncertainty as the result as being driven by sampling error, driven by potentially repeated experiments. When we get to confidence intervals and statistical significance testing, I think this will become more clear. Okay, so let's kind of take our coin flip example. Go back here. I flipped 3 coins. They all came up heads. And my frequentist approach would suggest that I should say that the probability of heads is 1 based on this result, right? Heads plus heads plus heads, 3 over n, 3. Probability X bar is equal to 1 in this context. Now, of course, I know there's sampling error on that, but I don't know how much it is right away. A Bayesian approach, by contrast, might say, you know what? I think this is probably a fair coin. And I have strong prior information that a fair coin will be heads half of the time and tails half of the time. If I flip coins and see different patterns, I could change my belief about the likelihood of a heads. Maybe I think the coin is not a fair coin. But it would depend on how much I weight what I observe versus what I already know, based on how strong that belief is that a fair coin will be 50% heads, right? So if I am absolutely certain a fair coin will be 50% heads, I will need a lot of data to convince me that this is not a fair coin. But if I have a weak belief that this is a fair coin, or if I have a weak belief that a coin will be heads 50% of the time, then maybe 10 coin flips will be enough to convince me that it's not 50%. Right? So I weight how strongly I believe something to be true, and then I observe the data, and then I update my beliefs based on what I observed. Right? This is the process of Bayesian inference. So beliefs are really critical. We can think of this as just subjective belief, but typically in a scientific context, we want to think about this as expert knowledge, right? We're kind of domain experts in our fields. We know about, for example, let's think about the relationship between employment and I don't know, involvement in the illicit drug market, right? And like selling drugs. If someone has a well-paying job, they're less likely to be involved in selling drugs, because we could think of all kinds of life course theory reasons why that might be true in a criminological framework, right? All kinds of, many different theories would give us different predictions on why we would see that association, right? But our prior might be that, you know what, I suspect that there's going to be less likelihood here for this group. This group is going to be less likely to be involved in the illicit drug trade because they have strong employment. By contrast, I'm going to project that people with less employment opportunity might be more likely to be involved in the illicit drug trade, right? And I can bake that prior knowledge based on old studies, based on theories, into my model itself, right? So I can effectively weight it. So even if my data comes off, because we assume that anytime we measure something, we're measuring with error, right? And so sometimes we really want to include this prior information in to adjust for the possibility that our data could themselves be nonsense, could result in nonsensical inferences, right? Now, of course, if we collect a lot of data, it'll outweigh our priors, right? If we collect a lot of high quality data, no matter what we believe, if the data is legitimate and we believe it to be legitimate, we will update our old beliefs, right? So the data still has a role to play. So that's the kind of 90-second version of Bayesian inference. But again, we're not going to dive too far into that this semester. I just want to introduce the idea. So I want to distinguish kind of in terms of definitions. When we think about statistics and we think about probability, we're thinking about processes that do not occur with certainty. We're thinking about what are called stochastic processes. Stochastic is another word for random, but you'll see it used, so I'm going to use it. S-T-O-C-H-A-S-T-I-C, right? In case you haven't seen that word before, stochastic just means random. And that means an event occurs, but it doesn't occur all the time. It occurs with some defined frequency, right? And it doesn't occur with some defined frequency. Deterministic processes, by contrast, do not include randomness. A deterministic process is non-random, meaning if I drop a ball, it will fall because of gravity, because gravity exists, right? Like every single time I drop this pin, it's going to fall. There's no randomness, right? It will fall. Now, once it bounces, where's it going to bounce? Then we could maybe introduce some randomness. But the idea would be with physics that if I have sufficient information, right, I could determine if I knew like, the exact slope of the table, the exact angle I'm dropping it at, all these, the exact height I'm dropping it at, I could with certainty determine where this pin is going to land according to Newtonian physics, right? Now, of course, physics these days is not actually there anymore. There is randomness in physics now, right? But the idea is that this is a deterministic process. I know with certainty this event will occur. We can think of the sort of deterministic processes as being relatively limited in scope, especially in the social sciences. We don't have a lot of deterministic processes in social sciences. But if a process does not include any randomness in it, we could call it deterministic. It is guaranteed to occur. It has a probability of 1 or a probability of 0. Stochastic events, by contrast, include randomness. For example, if I flip a fair coin, it'll be heads half of the time, right? And that's not to say that I don't know what's going to happen. I know it'll be heads half of the time. I have information, but I don't know what any particular event will be. I know that it has a 50% chance of being one outcome and a 50% chance of being the other outcome. I know what it will be on average, right? I don't know what any particular coin flip will result in. There's an element of randomness in it. So I can understand what will happen on large collections of this event, but I can't necessarily understand what will happen in any one event, or I can't necessarily project with certainty what will happen in any event. I can project with uncertainty what will happen in an event. So if we have uncertainty in something occurring, it is a random event. Random doesn't mean like we don't know what's going to happen. Random means it has some fixed probability of occurring, right? We could call that a stochastic event. Nearly all social processes have random components and can be treated as stochastic, right? So kind of thinking about this philosophically for a second, like let's think about your choice of going to graduate school, where you're going to graduate school, right? Now let's think about trying to build a statistical model that projects, will someone go to Rutgers or NJIT for graduate school, right? Now, the events that led you to the decision to come here and then enroll in this statistics classroom, right? There's tremendous numbers of variables that influence the decision to be here today, right? The decision to show up to class today. We could think probably for each of you, some set of like, I don't know, 100,000 variables that all led up to the course of your life that you're here today. Now, maybe we can imagine a universe where every single one of those is knowable, and we could actually plot out with certainty what would happen to individual lives, right? But a lot of people will suggest, well, humans still have choice, right? And so even if we do have perfect information on everything, there's still going to be randomness in the system because humans can decide to do whatever they wanted, not necessarily whatever they want within prescribed boundaries, but they have some agency, right? They have choice within these predefined boundaries. So we typically want to treat all social processes as random for two reasons. One, even if we think they're deterministic, the systems are too big, right? So we can treat them as effectively random. Sometimes when a system is too complex, we can't model the whole thing, right? If a system has 100,000 inputs into it, if there's 100,000 factors that are determining how a system works, it turns out we can use the laws of probability to make good guesses about what's going to happen. If we have the sum of many random events, that aggregate event will follow a discrete probability distribution, right? So this is a kind of cool feature of big systems, is we can use probability to model big systems. But in the case of humans, there's always going to be, randomness. And so even if like a kid's parents went to Harvard, there's like only a 5% chance that child will end up, in like the lowest income bracket and unemployed, right? Because class is inherited in the United States and like all the privileges that come with being a member of an economic or educated elite tend to adhere to children. There's still some chance that kid could just like totally go off the rails and do their own thing, right? Because humans can make choices. Also, like random events can really screw things up, right? So maybe there was like a really horrible car crash and that just threw the course of someone's life off in a trajectory. Some event that was not predictable, right? These kinds of things occur all the time. So nearly all social processes have random components and can be treated as stochastic, right? Just about anytime we're talking about anything involving humans, we want to treat the events as being driven by some random process. That is, we can almost never predict with certainty what humans are going to do. Almost never. Okay. So here's some definitions. That's kind of like philosophy of science stuff, but let's get to some definitions. An experiment. Yeah.
I have a question. So you said we can never, what someone can do. But what if you have a routine that every single day, this is what you do?
Well, we could predict that 98% of days the person will follow this routine. But what if it's, a terrible thunderstorm one morning, and despite this person goes out for their morning walk with their dog every morning, on this one day they don't because the weather's so horrible, right? So we could have an external event intervene, or maybe that person gets sick that day and doesn't want to go for the walk, right? So even if they do it very frequently, right, there's still some chance that the event will not occur that's driven by random external events, or maybe just that person chose not to do it this morning. Even if they very rarely do that, they still could, right? So even if that person 10,000 times follows their routine exactly, if they don't one time, it's not guaranteed to occur, right? Or we could think of it from the Bayesian standpoint, that person still could choose to not do that routine one day, right? And we know that because we know that humans can make different choices. So my prior tells me, even though they've always done this, I know that they could one day choose not to do it. So I'm not going to say this is guaranteed to occur. I'm just going to say it's highly likely to occur. So very likely, right, is a kind of less strong statement than guaranteed, right? Very likely means I'm going to see this more times than not, but there's a chance it won't happen. So we're going to use typically these kind of more imprecise definitions to talk about how events occur. We're going to say it's likely to occur, it's unlikely to occur, right? It'll happen most of the time, right? We can kind of make more conditional statements like that. I mean, we could think of human events that like we have very strong relationships, right? Like when you are hungry, you will eat, right? And there are some things where we could say there's maybe less uncertainty there. But typically, those kinds of processes are not the things we're directing our research toward. Okay, so an experiment is an action that produces stochastic events. An experiment is something I do or you do that produces an event that has some random component. A coin flip is an experiment, right? The sample space is a set of all possible outcomes of the experiment. So if my experiment is a coin flip, what is the sample space for my coin flip? What are all possible outcomes for a single coin flip? Heads or tails. My sample space, which we sometimes denote with omega, is a set of all possible outcomes of the experiments, that is, in this case, heads or tails. But let's kind of take this a step further. Let's say that our experiment is flipping 2 coins. What's the sample space? What's the sample space for flipping 2 coins? If we are paying attention to sequence, let's pay attention to sequence, right? One outcome could be heads, tails. One outcome could be tails, heads. One outcome could be heads, heads. One outcome could be tails, tails. Right? And those are all possible events we could observe. So we could observe a heads first or second, heads not at all, tails first or second, tails not at all. So we have 4 possible events that could occur from our experiment of flip 2 coins. That is, we have a sample space with 4 elements. There are 4 things that could happen. Sometimes this is discrete, sometimes it's not. Discrete meaning closed. Sometimes there's a fixed number of things that could occur. Sometimes there's not. But a sample space is a set of all possible outcomes of the experiment. An event is a subset of the sample space. So we could think of an event being, what's the probability of observing 2 tails? Well, the events in that case can be defined as this subset of the sample space, right? What if our event is we observe 1 tail flipped out of the 2 coin tosses? Then our sample space is these 2 events, right? What if our event is we observe at least 1 tail? Then our sample space is this subset. Then our event is that subset of the sample space, right? So we can define an event as some grouping of outcomes within a sample space. Could be a single outcome, could be a group of outcomes. So an experiment, I think we get this, but we can flip a coin, we could roll a dice, we could vote, right? Lots of different experiments are possible. Lots of different things we do in the world. The sample space for flipping a coin is obviously heads or tails. You'll note when I denote a sample space, I'll use these curly braces, and this will come with set notation. So anytime I'm describing a set, I'm going to wrap my set in curly braces. That is this one on your keyboard. It's the shift over the square bracket. Okay, so sample space for a coin flip is heads, tails. Sample space for rolling a single 6-sided dice. It's going to be 1, 2, 3, 4, 5, 6. Right? Those are the possible outcomes. Sample space and vote in a Democratic presidential primary could be I abstain, I vote for Harris, I vote for Biden, I vote for Warren, I vote for Sanders, or I vote for Castro. You can tell when I wrote these slides. Yeah, anyway. So we have choices, right? And we'll have a possible set of choices within an event. So we could, in this case, not participate, or we could vote for one of the listed candidates, right? So an event could be heads, tails, not heads, heads or tails, heads and tails, right? Or 2 heads. Yeah, we can think of lots of different event configurations for each of these. An event for the dice roll could be you roll a 3, you roll an even number, you roll anything but a 6. An event for the Democratic Party sample space could be you did not vote, you voted for a woman, you voted for a senator. Right? And we can think of different ways of subsetting the sample space based on how we define events within that sample space. So if all outcomes are equally likely, and n represents the number of elements of a given set, then the probability P of event A is defined as n sub A over n sub omega, where this is the number of events that fall into the subset A divided by the number of elements in the sample space, if each event is equally likely. So using that definition, let's think about the dice roll. Remind me what the sample space for a dice roll, 6-sided dice roll is? One, 2, 3, 4, 5, 6. Those are the possible outcomes. So let's call our events A, roll an odd number. So how many possible events could we observe that are odd numbers? 1, 3, 5. So n sub A is 3. What is n sub omega? How many elements are in the sample space? 6. Right? So P of A equals NA over N omega. What do we get? 3 over 6, right? We get 0.5. There's a 50% chance of rolling an odd number. That was easy. Let's try this again. So N omega we know is going to stay the same, right? Because the sample space is going to stay the same. Let's change our event out to roll a number divisible by 3. So how many numbers do we have that are divisible by 3 in our sample space? 2, right? We have 3 and 6. So how many elements are in the event the event A? 2. So we get 2 over 6, or 1 over 3. Right? We have a 1/3 chance of rolling a 3 or a 6. That is a number divisible by 3. So if all outcomes are equally likely, that is like on a fair dice, you have just as much chance of rolling a 1, 2, 3, 4, 5, 6. Each side on it has a 1 over 6 chance of being rolled, right? Or on a coin, we have a 1 and 2 chance of a heads or a tail, right? If all outcomes are equally likely, we can compute the probability of event A using this formula. So here's some axioms of probability. The probability of any event A is non-negative. Probability can never be negative. It can be 0. Right? If an experiment is conducted, the probability that one of the outcomes in the sample space occurs is 1. When we run an experiment, something will occur. And that something must be in the sample space. So you can think back to our coin flip, right? Heads, tails is the full sample space. People will argue, well, what if it lands on its edge, right? Which has like a vanishingly small chance, but like, okay, maybe that's in the sample space too, right? So the probability that something occurs in the sample space is 1. That is, we are guaranteed to observe something in the sample space. Here's the addition rule for probability. If events A and B are mutually exclusive, meaning A does not include any elements of B, so we can say that roll a number divisible by 3 and B equals roll a 4. Are those events mutually exclusive? Or is A roll a number divisible by 3 and B roll a 4? Are those events mutually exclusive within this sample space? Yes. Right? If B occurs, A did not occur. If A occurs, B did not occur. What if B equals roll an even number? Are these events mutually exclusive? No, because B includes 2, 4, 6, and A includes 6. So if A occurs, B could have occurred. If B occurs, A could have occurred. So this rule only applies to events that are mutually exclusive. That is, if A occurred, B did not occur, and if B occurred, A did not occur. But if we have P, and we can represent this as an OR, if either P, A, or B occurred, then the probability of either event is the probability of A plus the probability of B. We can add those two probabilities together. That is, what's the probability of rolling a 1 on a 6-sided dice? 1/6. What's the probability of rolling a 2? 1/6. What's the probability of rolling a 1 or a 2? 2/6. 1/6 plus 1/6, 2/6. Yeah? Okay. So that's the addition rule for probability. When events are mutually exclusive, we can simply sum their probabilities to obtain the probability that either event occurs. This is a really useful one. So the probability that an event does not occur is 1 minus. So the probability that an event occurs is 1 minus the probability that it did not occur, right? Because we define probability on a 0 to 1 scale. What's the probability? So let's say P of rolling a 2, where the sample space 1, 2, 3, 4, 5, 6. P of 2 is equal to 1/6, but we could also express this as P of not 2, right? I'm just using the exclamation because we use that in R, right? But we could express that as 1 minus 5/6, right? But probability of rolling anything but a 1 is 5/6. So we can use this rule of total probability, that is, everything has to sum to 1, right? This follows from the rule of total probability, which is here, outcomes in the sample space occurs must be equal to 1. So we have a sort of inverse defined by that. 1 minus the probability an event does not occur is equal to the probability of the event. Which this is probably intuitive for you, but it's useful to just lay it out. Right, this is the rule of total probability. The sum of A occurs and A does not occur must be 1. Right, we could think about moving P not A over to the other side, and then we get P of A plus P not A equals 1. Something occurs, whether it's A or something not A. Okay. And again, P rolling a 6 is 1/6. And we get 1 minus 1/6 equals 5/6. Okay, so law of total probability suggests that if P of A, we could obtain the probability of event A by summing the probability of events A and B plus the probability of A and not B. So let's assume that event A is eats pizza and does not eat pizza, and event B is happy and unhappy. This is me. If I eat pizza, I could do two things. I could eat pizza or not eat pizza, and I could be happy or I could be unhappy. And that's the full sum of events that could ever occur in my life. Okay, so if the probability of eating pizza is 0.5, and the probability of eating pizza and being happy is 0.4, then we can establish that the probability of eating pizza and being unhappy is 0.1. Let's work through that. P of A eats pizza, right? P of A and B eats pizza, happy, 0.4. P of A not B eats pizza, unhappy, 0.1. So if I have two sets of events, A and B and A and not B, the sum of A and B and A and not B must be equal to the probability of A. So I can obtain the probability of events if I have the probabilities of the event co-occurring with another event and the event not occurring with another event. I add those two things together, right? I get the probability of A. So it's a little confusing, but the idea is I can combine information about events co-occurring to sum all the possible combinations of events that could have occurred together to obtain the probability of another event. Right? The sum of things that could happen between A and B will be equal to the probability of A. The general probability addition rule is if I'm interested in knowing the probability that A or B occurred, right? If I want to know the probability that either A or B occurred, and here I think this is actually a place where like Venn diagrams get really useful. So let's think of A, B. I'm drawing a lot, so I'm going to flip my laptop over so people can see. No idea if that's in camera, so sorry for those watching at home. I will check. Good enough. Okay, so if we're interested in knowing PA or B, how can I represent that? Let's call this sample space omega. What can I shade in to represent A or B? Everything here. All of A and all of B, right? But I can't just add up A plus B, right? Why not? Why can't I just add up A and B to obtain the probability of A or B? Right, because there's this set of events where both A and B occur. So I'd be double counting those events, right? If I summed up the full circle A and the full circle B, these events here would get double counted. So the way I can accommodate this is by adding PA plus PB, add the two full circles, minus that slice in the middle where they overlap, minus their intersection, right? We call it PA and B. We would call PA and PB the union. So that full sum of the circle is the union, right? The intersection is this slice in the middle. Okay, so a permutation asks what patterns of X, Y, Z are possible if we draw two elements randomly. Someone help me out here. So if our sample space is equal to, no, we don't know what our sample space is, I'm sorry. But we have some set equal to X, Y, Z, and we know we're going to draw two elements. We would like to know every possible permutation that we can observe from drawing two elements. So we can just kind of start out by listing them. XY, XZ, YX, YZ, ZX, ZY, right? That's assuming we can't draw the same letter twice. If we could, we would have more, right? But that's our possible sample space for drawing two elements from this set. We could call each of these a permutation. Each of these elements we could call a permutation. So how many permutations, how many possible combinations of n elements are there when we draw K at one time? And we cannot draw the same element twice. This is a way for us to calculate how many permutations are possible. So in this case, we have three elements and we draw two, right? So what's n here? N equals 3. What's K? K is 2. Let's do the math. Let's see how many possible permutations we can obtain. N factorial over n minus k factorial. Okay, so a factorial, that is the exclamation mark, means multiply by the sequence of integers descending, right? So we would go n factorial equals 3 times 2 times 1, right? So we would get 6 in the numerator. And n minus k factorial would be equal to 3 minus 2 factorial, which is equal to 1. Because that's 1. 1 factorial is just 1. We don't go to 0. 1. So in this case, we get 6 as the number of possible permutations. Right? Let's try this if we draw 3. Oh, wait. Okay. So here's what the formula looks like, right? We say we can kind of read this as 3 choose 2 is kind of how you'll see this read sometimes. If we want to know what the number of permutations is for a sequence where you have 3 elements and we're choosing 2, we can use this formula to obtain the number of possible permutations. So combinations, permutations pay attention to order. That is x, y, and yx are identical combinations, but not identical permutations. So we can multiply this by k factorial in the front to obtain combinations. We're not going to do too much with combinations. This math gets messy really quickly, but I want to show you an example of kind of where there could be. So a combination, in a case of a combination, xy and yx are not distinguishable, right? So in the case of a permutation, they are, but in the case of a combination, they aren't. So we're not paying attention to order in a combination. xz and zx are identical combinations, but not permutations, right? So by multiplying the denominator by k factorial, we can obtain, in this case, 6/2 or 3 combinations possible, right? 6 permutations, 3 combinations. Sometimes you'll pay attention to these, and it's just kind of good to know the language. We're not going to use this math applied too often, but it's good to understand this kind of theoretically. So this is a classic statistics problem that I think is kind of fun. What's your guess? How many people do there need to be in a class for there to be a 50% chance that at least 2 of them have the same birthday? What do y'all think? You know. Okay, fine. So don't cheat. What do y'all think? How many people do there need to be in a class for there to be a 50% chance that at least 2 of them have the same birthday? Give me a guess. 15. Wow, okay. That's a small, okay, so like give me an informed guess. Like think about how many possible birthdays are there? 365, right? 366 if we're including leap years. So there's 366 possible birthdays. How many people would we need to have in a classroom for there to be a 50% chance that 2 of them have the same birthday? Most people might guess something like 180, right? Because you're kind of dividing it by 2 and thinking, well, yeah, at that point, we would have, you know, likely, we might see 1 overlap when we get 180, right? But let's kind of work through this. We can solve this problem using permutations. So let's assume each date of birth is equally likely. We know in truth that's not accurate, right? Births are seasonal. But if we assume that every person has an equal chance of having any date of the year as a birthday, by the complement rule, we can establish that is the probability of A is equal to 1 minus the probability that A does not occur, right? So probability of A is equal to 1 minus P not A. So the probability, in this case, our event A is 2 people share the same birthday, right? And we know that the probability that 2 people share the same birthday is equal to 1 minus the probability they don't share the same birthday. So we have K students in a classroom. How many ways can K birthdays be arranged if there are no duplicates? Right, that's our first question. And we can use permutations to figure that out. We can compute how many ways can we arrange K birthdays, right? Without repetition. So we have 365 factorial over 365 minus K factorial. Now, as I'm sure you probably know, 365 factorial is an absurdly large number. So just forget what the factorial function is. Okay, it's just factorial. So factorial 365 is R is telling me it's infinite. It's a huge number, right? Right, because we get 365 times 364 times 363, even just the first three elements of it, right? We're up to an obscenely large number. But it results in a very large number, but this is tractable mathematically using logarithms, right? But we're not going to worry too much about that for now. For a class size of 10, right, we would get 365 choose 20, 365 factorial over 365 minus 20 factorial. Right, so there are 3.7 times 10 to the 25th possible permutations for this set, right? That's massive. Sorry. Assuming all have unique birthdays, right? So because P of A is equal to the number of elements in A divided by the number of elements in omega, we can write the problem as probability that nobody has the same birthday. That's the probability that of K is the ways that K unique birthdays can be arranged, divided by the ways K possibly non-unique birthdays can be arranged. So we could actually divide this by the combination number and obtain the result. Right, so we could obtain it as 365 choose K over 365 to the K. So the probability that there's at least one duplicate birthday is 1 minus 365 choose K over 365 to the K, which can be written logarithmically, yada, yada. But here's the solution. For a class size of 10, we have a 12% chance that two people have the same birthday. For class size 50, we have a 97% chance that two people have the same birthday. Right? We can plot this out to think about how many people are in the classroom, and we wanted to know where that 50% threshold is. That 50% threshold is at about 22, 23. Right, so what's that?
15 wasn't that far off.
15 was actually not that far off. At 15, you've got about a 25% chance. Yeah. But at 50, right, you've got a 97% chance. And obviously this is going to converge to 1 as we keep going.
Can we see if anybody here is a birthday?
Sure. The chance though, we got 1, 2, 3, 4, 5, 6 of us. So, right, our probability is about, we'll call that 4%.
But it's possible.
It's possible. It's possible. That's about 1 in 20. I'm July 28.
October 27.
November 29.
Okay.
February.
Okay. That's a no. But like 3 days off on one of them. Yeah.
When's your birthday? Oh, Halloween.
Halloween. Wow.
Nice.
I don't know if that's a thing in not America, but
Yeah.
it's cool here.
Okay. Let's take 5 and we'll come back and we'll continue in just a moment. That's the birthday problem. All this is intended to do is not to show you how to compute probability, but to show that you can get counterintuitive results when we apply the laws of probability.
do we have class next week?
A lot of people were asking that. I will hold class, but it will be recorded. Attendance is optional. So would you prefer not to?
No, I'll be here. I have a presentation right after this class.
Okay, so yeah, typically classes are canceled Wednesday on, not Tuesday on. It's kind of tradition in our department to cancel class the week before because of the criminology meetings. But we already missed a week this semester, so I'm not doing that.
But the week after, like Tuesday the 30th, is the day after my birthday, so I'm not going to be
Reasonable. Take that day.
here. Okay.
You enjoy it.
Yeah, I took my birthday off this week.
Yeah, sure. Sleep it off.
Well, I plan to drink, so you know.
I understand.
I'll be awake the next day.
Yeah, no, sleep well. Recover. There's where we were with the birthday problem. Now, the exact solution is available there, albeit it's not simple to calculate, but we can do it. But let's say that we don't know the formula for permutations and total probability, but we still want to answer this question, right? We can actually do that with simulation, right? We can use our computer to estimate this probability. The way we could do that is by just drawing random birthdays, right? And then comparing after we draw random birthdays, whether there are matches, right? So I'm going to make a sim bdays function. This is my simulation function where I'm going to sample, and I'm just going to pretend that leap years don't exist, but because technically they're 366, but we'll just pretend that 365 is the number. What I'm going to do is I'm going to sample, use the sample function to draw a random digit between 1 and 365. I'm going to do that k times, and this replace equals true argument tells R that if I draw one number, put it back in the bucket. So what sometimes we can sample without replacement, meaning I could draw 2, which means on the next draw, 2 is not possible. Or if I draw 2, I note it and then I put it back in. I could draw 2 again, but it has the same probability of being drawn, right? So replace equals true, sampling with replacement means that we could draw the same element multiple times. And we want that here, right? People could, in theory, have the same birthday. But we're going to draw k random birthdays, where that's going to take on a value between 1 and 365. And then I want to use this kind of funky function to tell me whether or not there were any duplicates, right? So I'm going to say, what's the length of unique days? Unique days is going to return how many unique values there are in the vector birthdays. And if that vector is less than k, then that means there's a duplicate, right? So if I have 10 birthdays drawn, k equals 10, and I have 10 different birthdays, this function will return 10, k is equal to 10, false. If one of them is duplicated, then I'll have 9 unique birthdays, 9 is less than 10, true. So this line of code will return true when there's a duplicate and false when there's not a duplicate. So if I send bdays 1, obviously I'm going to get false. I only drew 1. Obviously the length of unique days is going to be 1. K is equal to 1. We're good. If I send 366 birthdays, I'll get a true for sure, right? With virtual certainty. The probability is not exactly 1, but it's like dang close. Okay, so let's kind of work through this. What I'm going to do is I'm going to iterate over k class sizes, right? And then I'm going to repeat the experiment many times. What this is called Monte Carlo simulation. So sometimes when we don't know the exact estimate for a probability, we can use a simulation procedure to generate an approximate estimate. Right? So if we understand how the process works, we can use our computer to simulate the process many times to obtain an approximate result. And I say approximate because there will be some sampling error there. We call it simulation error in this case. Right? That is, just because we're drawing random numbers, we're going to be off from the truth by some amount. We don't know exactly how much. We can compute the range of the possible error, but with a large enough number of simulations, that error is going to be pretty small. Okay, so what we're going to do is we're going to repeat each of our class sizes 100,000 times. So I'm going to take a class size of 1 and draw it 100,000 times, right? And take a class size of 2 and draw it 100,000 times. So what I'm going to do is I'm going to repeat each class size 100,000 times. And what I'm going to do, because of the law of large numbers, right? When I've done that 100,000 times, the mean is going to converge to the true probability, right? It will become very close to what we would have observed with the exact calculation. So I need to do this with a loop. I haven't shown you loops before in R. They're not something I'm going to want you to use too often. This is code I'm just showing you to illustrate how it works. I don't expect you to replicate this, but it is 100,000. So that's the number of simulations we're going to do. K is 30. That's the range of class sizes we're going to observe. Actually, in this case, we're just going to do one class size. We'll loop over K next. But sames is going to be a vector that holds missing values. I need to initiate it just as length n. So it's going to be 100,000 long vector. Right now, it just holds empties, right? And then we're going to simulate 30 birthdays and ask whether any of them are the same, right? Using our sim bdays function from before. So this vector is going to contain 100,000 true and falses, right? True if there are duplicate birthdays, false if there are not. So the Monte Carlo solution to this, where we repeat 30 class sizes 100,000 times and ask if they have the same birthdays, the average comes out to 0.705. The exact solution using our birthday function where we use the permutation formula is 0.706. Actually, with rounding, this is 0.706, this is 0.706. Those solutions are indistinguishable. A very, very small amount of simulation error there. This is called, we call it simulating. You can also hear sometimes people call this a brute force solution, meaning you're just going to like run the experiment over and over and over again and see what happens, right? But we can simulate it using the Monte Carlo method, named after the casinos, right? But we can run the experiment many, many times and obtain an approximate result if we don't have the exact result available to us. And in this case, there's no meaningful difference. And for a computer, even though this is 100,000 simulations, if you run this code on your computer, it'll take a fraction of a second, right? Computing is very powerful, so simulation is often great. So this is with 1,000 simulations per K. Here's the class sizes from 1 to 50. And I effectively looped that simulation over each class size 1 through 50.
Professor, if you simulate like over and over, it's going to give you different results every single time.
Yes, but it's going to wiggle around. We can think of it kind of like this. So we have simulation error every time. That's exactly right. But what we'll see is, let's imagine that on here, this is like the iteration of the simulation. We'll say this is like 0, and in this case, we're running 1,000 of them. And this is our estimate. Call it X bar. And let's say that this dotted line is mu. Our estimates from a Monte Carlo simulation will center around mu. What we're typically going to see is something like this. Random noise jumping up and down around the truth. That's what we want to see. And that's typically what we're going to see. When we get into like more complicated models, you're actually going to have to look at these and be like, oh, is there a pattern here? If there's a pattern, our model's no good, right? But if there's no pattern here, meaning we have a fixed band within which the errors occur, and it doesn't depend on which iteration we're on, then we just have random noise. And that's fine, because if we average over this, right, we're going to get an estimated bar that's really close to the truth if we take the mean of all of those values. So yeah, every time we run it, and you can see that here, right, we get slightly different values every time. But the approximate shape of the curve, the shape of the curve, right, is similar to the shape of the exact curve, right? The curve we obtain with only 1,000 simulations per K is very similar to the exact curve. And once I increase that to 10,000 simulations, once I increase the power of my simulations, right, then the curve becomes very, very similar to the exact curve. If I crank it up to 100,000, you can imagine that it would follow it nearly identically, right? What happens is as I increase the number of simulations, right, here's the truth. So when I only run 10 simulations, we can imagine that my uncertainty per room might range around there, right? That I might have a lot of uncertainty, that the results could go from here to here to here to here to here to here, right, et cetera. But as I increase the number of simulations, this is going to be my estimate. We can think of this band as the possible estimate of the average, right? So when I don't have a lot of simulations, my possible estimate of the average is pretty wide. When I do have a lot of simulations, these extreme values become less likely to be observed, right? And we're going to decrease the range of the band. So as our simulation size increases, or our sample size increases, the range of our possible estimate for X bar shrinks. We get closer to the truth. Now, we don't know exactly if we've landed on it, if we've landed on the exact truth, but we know that the possible amount of error that we could have generated gets smaller the larger our n gets. Right? So if my n is 100,000, my range of uncertainty might reduce to that. Right? This looks maybe we're getting a little ahead of ourselves, but as our n increases, as our sample size increases, our uncertainty decreases. And that's true across the board for all kinds of uncertainty. But simulation uncertainty, that's certainly the case. We can see here, right, when we went from 1,000 simulations to 10,000 simulations, right, the amount of error that we observed decreased pretty dramatically, right? And one way to describe that is that our uncertainty decreased. We are more certain that the line falls here, and we know the truth. We can compare this to the exact line, and this looks much closer to it. We reduced our error. Typically, when we're running a Monte Carlo simulation, 10,000 is usually enough to get a pretty accurate result. 100,000 if you want to be certain, 1 million if you want to be really certain, right? But there's not much cost to that, right? So let's check out this simulation code for a second. So here's our birthday. Never mind. We'll move on. I'm sure you believe me. If I increase my n, the amount of time it takes R to run these numbers of simulations is pretty small, right? It doesn't actually take a dramatic amount of time to do this, despite it being a really large number. Computers are good. Okay, so let's move on to joint probability. Joint probability is the probability of two events occurring, PA and B. We already talked about PA or B. What's the probability that A or B occurs? But maybe we want to know the probability that both A and B occur, right? So if we go back to our Venn diagram, the and component is the intersection A or B is the full area A plus B, right? Minus A and B. A and B, just a little slice in the middle. So A or B is the sum of all of this. A and B is just this little bit in the middle, the intersection of the two. Okay, the marginal probability of an event B is P of B. In that case, it's just the circle B, right? We call that the marginal probability. The conditional probability is the probability of event A occurring, given that event B did occur. And we write that with the vertical bar. So we can read off this formula, P of A conditional on B. Knowing that B occurred, what's the probability of observing A? Right? So conditional on B, when B is true, how likely is A to occur? So in this case, we kind of have the answer looking at our Venn diagram, right? If B occurred, what's the probability that it was A? What's right here, right? But we can compute this as the probability of the intersection A and B over the probability of B. So how likely was B to occur, right? We're going to divide our intersection by the probability that this event occurred in the first place. And that will give us the probability that A occurs when B occurs. And that will be less than just the probability of A and B, right? So the conditional probability, the idea here is that when we are conditioning, we have information. We know B occurred, right? So we're eliminating everything that's not B from the sample space, right? Everything that is not B can't have occurred if B occurred. So we have the joint probability P A and B over the marginal probability of B. That's the definition of a conditional probability. If B occurred, how likely is it that A and B occurred, right? And we can think of this, right? The probability of A and B generally is just this region, right? That's a relatively small subset. But when we condition on B, we reduce our sample space to just B. Knowing that B occurred, now this area is a much larger proportion of B than it is of omega, right? So the fraction, the ratio of this to this is much, much larger than the ratio of this to this. That's what we're after. If I know B occurred, how likely is A to have occurred? Now, conditioning is a really important concept in statistics. Effectively, when we run a regression model, we're computing conditional probabilities. When we run a regression model with predictors, we are computing conditional probabilities. So let's look at some voter data. I think I would need to give you this. So let's just follow along. I don't know if you can load this in, but we'll just follow along on the slides. So this is data from a national election survey. And we're going to look at patterns of likely voters, patterns of voters in Florida, right? Demographics of voters in Florida. So let's ask a question from this data set. What's the probability that a randomly sampled voter in the population is Black? Assuming that we have the full population. What we can do is we can use the count function, or we could group by and use the n function. We can count the number of voters in each group as a proportion. So in this case, the sample includes 2% Asian voters, 13% Black voters, 13% Hispanic voters, 0.3% Native voters, 3% other, 70% white, 68% white voters. So what's the probability that a randomly sampled voter in the population is Black? We can use this contingency table. That's what this is called. This is a contingency table. To just read off what proportion of voters in the population are Black. And if I draw one at random, then it's just going to be equal to exactly the proportion in the population. In this case, 13%. This contingency table can tell us the likelihood of an event occurring. We only need two pieces of information. We need the number of individuals in the focal group for the event, and we need the total size of the sample space. Right? So in this data, if we sum the voters column, we get the total number of voters. And then we can divide 1194 by the sum of this column to obtain the proportion. In that case, the proportion is going to be exactly equal to the probability of sampling a random voter in that category. What's the probability that a voter is a woman? Well, we're going to count gender and compute our contingency table again. We'll see that we have 54% women, 46% men. Yeah? So we're clear on probability being equal to proportions in this context, right? Okay. So what's the probability that a voter is a Black woman? What is the probability of being both Black and a woman in this data? Well, we can count by gender and race. We can make a two-way contingency table. I'm going to do some fancy coding to make it look right, but we can then count up what proportion of voters are in each group. Now, the sum of all of these values should be equal to what? The sum of all of these p's is equal to what? In our count by race of voters, what's the sum of all these probabilities equal to? 1. That's our sample space, right? So you have to belong in one of these categories according to the data, right? 1 and only 1. Of course, in reality, it's more complicated than that, but this data is defined that you must be in one and only one of these categories. So the sum of p is equal to 1. The sum here will also be equal to 1. Now we've done a two-way table. So the sum of these two columns will be 1. Right? We're representing what proportion of voters are in each of these cells. We can call each one of these a cell, right? So we have about 1% of the electorate is Asian female, 1% Asian male, 7% Black female, 6% Black male, right? 7% Hispanic female, 6% Hispanic. Anyway, you get the idea. So what's the probability that a voter is a Black woman? Right here, 0.07 out of this sample, if we draw one individual. So what's the probability that a voter is a woman if we work from a table like this? Right? Now we have the same table as before. We have the proportion of voters in each racial group by sex. And we want to know the probability that a voter is a woman. How do you think we could obtain that from this table? We could sum up, pretty trivially, the values in F, right? We could sum up these values to obtain the probability that the voter is a woman. But we can also think of this using the law of total probability, right? So we can think of the probability that a voter is a woman is the probability that a voter is a woman and B plus P and not B, right? So B in this case we can think of as race. So what's the probability that a voter is a woman and Asian, and a voter is a woman and not Asian, right? And that will be equal to the probability that a voter is a woman. And in this case, we have both of those quantities. So we can sum over PA and B, PA and B for all B's to obtain P of A. So that is if we have a table of joint probabilities, that is the person is in both categories A and B, we can sum over each of those probabilities to obtain the marginal probability of A. We can sum over joint probabilities to obtain a marginal probability of A. Conditional probability works a little differently. If a voter is a man, what is the probability that he is Asian? So we know the voter is a man. We can compute this using a table quite easily, right? Just by filter to men, count by race, and then divide the number of men in each race by the sum of total men, right? And so we can kind of read that off as 0.02. But we could also use the rules of probability to compute this if we don't have an exact table. We could use the definition of conditional probability as the ratio of the joint to the marginal, right? So the probability, knowing that someone's a man, that person is Asian, is equal to the probability that someone is Asian and a man in the full data, divided by the probability of being a man. So we can go back to this table to solve that. So what's the probability that someone is Asian and male? 0.01, right? So P we already have the information we need to do this. Okay, so we have P, A, and B equals 0.01. And then what's the probability that a voter is male? 0.46. So we can compute that ratio to obtain the conditional probability without actually doing the table itself, right? If we have those two pieces of information, the proportion of the sample that are men and the proportion of the total sample that are Asian men, right? We can effectively divide the proportion of the total that's Asian men by the proportion of men in the total to obtain that conditional probability. If I draw a man, how likely is it that that man is Asian? Well, following that formula, or just by computing the contingency table, we get 0.21, 0.22. Okay. So we can also condition on more than one variable. What's the probability that a male voter over age 60 is white? right? So we may want to know if we have a male voter over age 60, we know that conditional on the voter being male and over 60, what's the probability that that voter is white? Now, in tidyverse terms, what we could do, we could actually do this a few ways. We could run a filter, or we could do it with a mutate. I'm going to mutate over 60 equals age greater than 60. I'm going to count over 60 by gender and race, and I'm going to compute proportions. And so I'm going to end up with this contingency table. So true here is over 60, white 0.124, right? So if a voter is male and over 60, we obtain a conditional probability that is, we got about a 12% chance that voter is going to be white. Okay, so in general, we can extend the logic of our definition of conditional probability by adding in more joint events here. So the probability of event A and B occurring, conditional on C occurring, is the joint probability of A, B, and C divided by the marginal of C. Right, the marginal is our conditional here. Or if we want to know the probability of A, conditional on B and C, we take the joint probability of all the events occurring divided by the probability of the condition. Okay, that's a lot, but just remember the idea of conditional independence is the idea of what's the likelihood of an event occurring if we know something else already happened. The idea of joint probability is what's the probability of two events occurring if we add those two possible events together in the sample space. Think of that as the A and B Venn diagram, right? Okay, independence is a pretty important concept in statistics, right? We have two events are defined to be independent if knowing one event occurs gives us no information about another event occurring. Two events are independent when knowing that one event occurred tells me nothing about another event occurring. I gain no information from it. So we can define that mathematically as P of A conditional on B is equal to P of B. That is, conditioning on B tells us nothing about A. The probability of A conditional on B is equal to the probability of B. And that's true if and only if PA and B is equal to PA times PB. Right, so we can obtain the joint probability of two events A and B if they're independent by multiplying the marginal probabilities A and B. So are race and gender independent in voting in Florida? This might be a question we're interested in asking. Does the likelihood that a man or woman votes, does that differ across racial groups, right? So we can run an independence test. If it's independent, then we should observe that the probability of being black and male is exactly equal to the marginal probability of being black in the data times the marginal probability of being male in the table, and so on for other groups, right? So let's run this independence test. First, we're going to compute those conditions. We're going to compute the marginal probability of being male by summing over all joint probabilities of being male by race, right? So we'll sum this male column to get the marginal probability of being male from our joints. Remember, we can sum up each A and B to get the probability of A. So we'll sum over male. And then we'll sum over our race table. We'll kind of compute that by adding the M and F column arbitrarily. But here we'll get the proportion for each racial group. So we get 0.131 for black. We get 0.464 for male. Now we can examine whether the joint probability of sex and race is equal to the product of the marginal probability with a plot, right? So obviously y equals x is our independence test, right? If y is equal to x, then we have independence. Because we're saying that PA times PB is equal to PB. So we have P race and male, P race times P male. So in this case, we can see that for the group other, the group Asian, and the group native, those fall more or less exactly on the line. The group Hispanic, we see some slight dependence. The group white, we see some slight dependence, and the black group is actually just, you can see a little yellow overlap there. So there's they're pretty close to the line, but there's some slight relationship there, right? That the proportions of men and women voting does differ a little bit by race. The two variables are not strictly independent of each other. Okay. Bayes rule. Okay, independence. We could call this, let's kind of take a second on this. So I think the best way to think about independence for me is to think about it in terms of information, right? If two events are independent of each other, learning about one tells us nothing about the other. So let's think about events being independent of each other. Is it being cloudy and it raining outside? Are those two events independent of each other? No, right? If I know it's cloudy outside, do I get information on whether it might be raining? Yes, right? Because in order for it to be raining, it must be cloudy, right? So those two events are non-independent. They are dependent on each other, right? To observe one, I'm more likely to observe rain when the conditions are cloudy. I'm not guaranteed to observe rain when the conditions are cloudy, but I'm more likely to observe rain when the conditions are cloudy. So this dependency-independency concept is really, really important in statistics. You're going to see the language come up in regression a lot, where we assume that predictors and models are independent of each other in order to trust those parameter estimates, those betas, right? We must assume that those variables are independent of each other. Often that's not the case. But independence, I think the best way to think about it is information. If I know B, do I learn anything about A? If I know A, do I learn anything about B? So in this case, if I know race, I actually learn a little bit about whether someone is likely to be female or male, right? So if I know race is one of these three categories here near the bottom, I don't learn very much, right? But if I know race is Hispanic, I know that the voter is slightly more likely to be male. And if I know race is white, I know the voter is slightly more likely to be female. It's not much information, but it's a little, right? Actually, yeah, I think that's the opposite. I think white, it's slightly more likely to be male. Black and Hispanic, it's slightly more likely to be female. But I learn a very small amount of information, right? I can make a better guess. So, you can think about this as like, if you had to place a bet on it, right? If we have independence, learning that a voter is Hispanic tells me that I should put my bet on that person being female, right? Even if it's a very small amount of leaning in that direction, it will pay off under repeated trials. Okay, so Bayes' rule is another axiom of probability we're going to work with. So recall that a Bayesian perspective treats probability as subjective, right? So we treat probability as our understanding of how likely an event is to occur, our belief in how likely an event is to occur. We're not appealing to repeated trials. We're just saying, how likely do we think something is to happen? That's what probability is, right? Probability is how likely I think an event is to occur. So Bayes' rule formalizes how we should update our beliefs based on evidence, right? So this is Bayes' formula. You can see it in a lot of different iterations, but there's a probability of A conditional on B is equal to the probability of B conditional on A times the probability of A divided by the probability of B. Now this looks wonky, but it works really, really well. So if we have a prior belief that an event A has a probability of A chance of occurring, we can put that here in our formula, right? We can call this our prior belief. Marginal probability of A is here. Then we observe some data represented as event B. We collect that data. So here's the data, and we're going to condition that on A. We can obtain a posterior probability A conditional on B, right? So effectively what we can do is we can take the product of our beliefs and the data conditional on the statistical model we use for the data to obtain our posterior probability A conditional on B. That's called updating, right? We update our beliefs using the posterior probability. But let's kind of, Bayes' rule is a bit complicated. So, and it's one of those places, kind of like the permutation result, where this is it's going to give us counterintuitive results. But we should start to fold it into how we think about statistics. So how good is a mammogram at detecting breast cancer? That's going to be our question we're interested in here. So here's what we know. We know that 1% of women have breast cancer. That's our prior, right? We know that from other studies, right? We look at vital statistics, we look at hospital records, and we see that 1% of the population has breast cancer, of women. We know that 80% of people who have cancer and take a mammogram test positive. And we know that 9.6% of people who take a mammogram and get a positive result when they do not have cancer. So let's kind of express this in our probability terms. So here, what should we define as event A? Event A, cancer, right? Event A, P of A has breast cancer. P of B equals test positive on a mammogram. Actually, these are not P, these are just the definition of the events, I'm sorry. Okay, so event A has breast cancer. Event B, test positive on a mammogram. So we define in the population the probability that any woman has breast cancer is what? No.
0.01.
1%. So any random woman sampled from the population has a 1% chance of having breast cancer. That's our prior information, right? We know going in that there's a prevalence of this disease. It's about 1%. Okay, now we know that 80% of people who have cancer and take a mammogram test positive. How can we express that using a conditional probability?
B equal 0.8%.
P of B conditional on what? Conditional on A. So it's not just P of B. P of B conditional on A, because we're saying 80% of women who have cancer and take a mammogram test positive. So the probability of testing positive, conditional on having cancer, 0.8. What's this last one? 9.6% of people who take a mammogram get a positive result when they do not have breast cancer.
It's just P of B?
No.
P of B. Given not.
So P of B conditional on not A. Six. Okay. Actually sum up, but we'll work with it. Okay, so how can we convert this? Slightly wrong. Okay, so our question is, if you take a mammogram, conditional on B, what's the likelihood that you have cancer? That's what we're after. right? That's the test we want to know. When we take a medical test, we want to know the probability that I have cancer conditional on a positive. We might also want to know 1 minus P of A conditional on B. What's the likelihood that I have cancer and I test positive? What's the likelihood that I test positive and don't have cancer? So that's our false positive and false negative rates. So we know 1% of women have breast cancer. We know 80% of women who have cancer will test positive. And we know that 1% of women will test positive when they don't have cancer. So using Bayes' rules, we can put this all together, right? So we can compute, we have PB A 0.8. So the numerator for Bayes' rule, P of A conditional on B is equal to P of B conditional on A times P of A over P of B. Okay, so we know the numerator, right? The numerator is PBA, so we have equals 0.8 times 0.01, right? So effectively, what we're getting is the likelihood that you have cancer and test positive, right? That both of those events occur. And so that's about a 0.008 chance, right? Divided by the probability of B occurring. Now that's a little trickier. We don't have that given yet, but we can use the law of probability, law of total probability to rewrite the denominator in a bit of a funky way. Typically, when we're doing Bayesian inference, we kind of ignore the denominator because the probability will be proportional to the numerator. The denominator is just a constant. But here's how we can compute it, right? We can use that law of total probability to multiply PB conditional on A times PA plus B not A times P not A. And we can obtain this result, 7.077%, right? So the probability that someone has cancer, given a prior probability of having cancer. So, okay, if I get a positive result on a mammogram and my prior is accurate, 1% of the population has breast cancer. If I get a conditional result, I should believe that I have about an 8% chance of having cancer, conditional on that positive result. I went into it believing I had a 1% chance of having cancer. After I get that positive result, I should believe that I have an 8% chance of having cancer, according to Bayes' rule. So I've gained information, but because the test is relatively weak, it only detects cancer 80% of the time, because it's not a particularly strong test, it doesn't change my information dramatically, right? Because there's a good chance the test is wrong. So I update my belief from a 1% chance P of A to P of A conditional on B, 8%. And this is counterintuitive, right? You've got a positive test. And we see this, well, it's like you have an 80% chance of detecting positive if you have cancer, right? That sounds good, but the problem is that cancer is rare, right? So these numbers are not like strictly accurate, so don't use these to make medical decisions. But if the overall incidence of the disease is rare in the population, and the chance of getting a positive is relatively low, and the chance of getting a positive when you don't have it is non-zero, then we're not actually going to get especially strong information from the test, right? We're going to go from assuming our risk is 0.01 to assuming our risk is 0.08. So there's still a 92% chance that you don't have cancer. But before you thought it was a 99% chance you didn't have cancer. So what you'll probably do then is go and get a more refined test, because if we increase that probability of testing positive conditional on having cancer, if we have a more sensitive test, that posterior probability will be much higher. Medical testing is really complicated. We talk about it in terms of false positive and false negative rates when we describe these things, but the sensitivity of the test also depends on how likely you are to have the disease in the first place, right? Okay. So that's a lot of math, but your homework, and I'll post the link on Slack, is to read 3 sections of the Open Intro to Statistics textbook, which is free. You'll have to just do a quick registration on this site, but it's a free textbook. I want you to read those 3 chapters and then complete the exercises listed here. You can do it in you can do it by hand if you like, and you just submit me a photo of your homework, or you could do it in R using R Markdown if you want to just write out the equations and do it that way. Either way works. Cool. Any questions? We're doing more of this next week. Sorry, but we're going to do 2 units on probability, and then we're going to flip back and finish the semester talking about uncertainty, which is going to get us back to regression models. But we need to understand probability to understand the full interpretation of a regression model. So the rest of the semester, 1 more of this, and then 2 units on uncertainty and regression. We're getting close.
So this homework still due next week.
Yeah.
Okay.
Yeah. So this homework will be due next Tuesday. I will hold class next Tuesday, but again, it'll be recorded and posted. So, if you want to skip out on attendance, that's fine. Cool. Any questions? No? Thank you for bearing with me. I know a strict math lecture is not the most pleasant thing in the world.